Thank you everyone for joining me. And so this is going to be my talk on TMR, which is towards an automated TMR EDA flow for Yosys. So if this will work for me. So first of all, in the introduction, I just like to give a little bit of a sort of agenda about what I'm going to cover today. So I'd briefly like to introduce TMR and the literature around TMR. Then I'm going to give an overview of how the Tamara TMR algorithm works, and then a discussion of what sort of worked in my one-year research thesis and what didn't work, and takeaways and future research directions to look into. So here's a little bit about me. I'm a fifth-year Bachelor of Computer Science honours student, which is sort of kind of postgrad in Australia. I graduated my Bachelor of Computer Science honours, undergrad last year. I also work part-time as a software engineer at Emerson, which is a drone robotics company, which is pretty disconnected from the stuff that I do in my research. But yeah, so of course I'll be covering today my research thesis on fault-tolerant EDA. I'm generally passionate about computer engineering, retro computing, optimization, a bunch of other things. And I'm applying to start a PhD at Macquarie University next year in Sydney. So when we talk about TMR, the main motivation to actually get into this is that when we want to deploy ASICs and FPGAs, not just terrestrially, but also in space, they can basically be subject to these things called single event upsets. And single event upsets are chiefly caused by ionizing radiation, as you can see here, coming through and actually striking a transistor, which will, in essence, through complicated sort of semiconductor physics, will cause a bit flip, which basically injects a fault into the system. So there are existing methodologies to protect chips from SEUs, but these are typically very expensive. So one example is the RAD750 CPU, which is used in the James Webb Space Telescope, as you can see here, the Curiosity Mars rover, many others. But this can cost more than $200,000 US dollars. So it's quite expensive. So basically, TMR is a technique where, so the RAD750 is a rad-hard sort of by design, but also by process machine, and that's why it's so expensive. Whereas with triple modular redundancy, the idea is that you can sort of use the device and then basically replicate the elements 3 times and have that connected up to a majority voter, and that will then perform the sort of filtering for you to make sure that the device is secure and safe from radiation. So of course, TMR can be added manually, but this is typically quite time consuming and also error prone. So the question is basically, can we automate this? And my idea was basically to implement TMR as a pass in an EDA synthesis tool, which means that it's integrated with the rest of the flow, it's easy to use, and hopefully fully autonomous as well. So the overarching goal is basically to pick any design of any complexity, sort of press a button and have it be rad-hardened. So Yosys is basically the best and the only open source research grade EDA synthesis tool. And when you want to do research like this, where you want to modify a synthesis tool to add a particular new behavior to it, you basically have to immediately discard proprietary tools like Synopsys, Cadence, Xilinx, and those, because they can't be extended to add sort of custom passes, which is like what I want to add. So basically, when you want to add TMR in the literature, there's basically 2 main paradigms to add triple modular redundancy. The first is what's known as design level approaches, which I think of as thinking in terms of HDL. So the question is, how can we modify HDL source code to actually introduce these sort of redundant copies of bits and pieces of the HDL? The alternative approach is netlist level approaches, which are basically I think of as thinking in terms of circuits. And the reason why I think netlist level approaches are better is basically when you're in design level approach world, you can run into problems with the tool deciding to optimize out bits and pieces of your redundant replicas, because they are, of course, redundant. But we'll get into that a little bit later. So now I'd like to give a brief description of the algorithm that I came up with. As I said before, I view netlist level approaches as generally better, and that's why TMR is mainly netlist driven. The voter insertion and the voter placement are basically inspired by two of sort of the main prior works in this sector. And you can see that Yosys runs after technology mapping in Yosys. This is a bit of a simplification. It doesn't exclusively run entirely after ABC, for example. It runs a little bit in the middle, but for this sort of overview, it's suffice to say it runs basically after technology mapping. So one of the important things to talk about in TMR is to understand this topic, this concept of something called a logic cone. So basically, a logic cone is a set of combinational circuitry that is encapsulated by either an I/O, so something on the edge of the circuit, or more commonly some flip-flop, so a sequential element. And you can sort of see what this looks like here, where you have these logic cones, which is sort of any amount of combinational circuitry that's bounded by then a flip-flop. So this is the general overview of how the TMR algorithm, which I came up with for the thesis, works. It's relatively straightforward in that we basically first analyze the RTL-IL from Yosys to sort of construct a data structure that we can more easily work with. Then we basically perform a backwards breadth-first search from the outputs all the way back to the inputs. Then basically there's a process that lifts sort of these low-level RTL-IL primitives into higher-level TMR primitives, which then get bundled into logic cones that are replicated and have voters spliced in. The circuit gets rewired, and then we look if we can find any successes. And from there, the process basically repeats until we have no more successes, which will happen once we reach the input edge of the circuit. So in terms of how the actual plugin itself is structured, this is the general overview. So the root sort of data structure node is this TMR graph node, which has children that can be IOs, wires, cells, and of course a subclass of a cell is a flip-flop. And I sort of distinguish between, it's a bit different because in RTL-IL, I'm pretty sure if I remember correctly, a wire is a sort of a cell maybe. But here I sort of distinguish between things that connect other things, so a wire, and then also just things that are particular logic elements. And these all get bundled up into a logic cone element. I then have things that can walk the circuit and provide sort of like fixes to the circuit and that type of stuff. And then I also have the main sort of plugin pass command and also the voter builder, which will actually build the voter class, or will build the voter circuitry. So speaking of voter circuitry, basically, this was where I sort of started out with in the design of the algorithm. I basically manually built the voters the old-fashioned way. I wrote up a truth table on a whiteboard and then used kernel mapping, in this case via Logisim, to basically construct out what the circuit should look like. And then I mapped that into Yosys, basically using a set of macros. So I pretty much looked at this diagram manually and then just typed them all up into C++ via macros. So on the algorithm as well, after the sort of voter, the first thing that the algorithm comes to do is do this RTL-IL netlist analysis. In RTL-IL, the connections between wires and cells are not immediately available, at least that I could see. So you have to do some sort of processing yourself in order to sort of figure that out. So I basically perform what you could call like a little bit of a sort of budget topological analysis to form data structures that we can sort of more easily work with. And in this case, I have a RTL-IL wire connections sort of struct that maps between, say, an object and two other objects or n other objects. And it's also important to talk a little bit more as well about the actual backwards breadth first search. So if we want to construct logic cones themselves, we basically need to find these combinational logic primitives between the two sequential logic primitives or the edges of the circuit. And again, this is important, and it might not be immediately clear, but the reason why we consider circuits using logic cones is because it means we can replicate them without changing timing. So if we are not careful with how we replicate flip-flops, we can easily introduce more flip-flops on a single sort of path, and then that can totally change the timing of the circuit in terms of like clock edges and stuff like that. So I perform a BFS from each output cell or each output sort of node of the circuit all the way back to the input. And the reason why I do this is because I do it under the assumption that each input to the circuit will naturally depend on whatever combinational and sequential path there is through the circuit from the outputs all the way back to the inputs. The other way around, I believe, may not necessarily be true. And this is what Beltrame does in his paper as well. And so when we reach an I/O node or a flip-flop node, and an I/O node is just what I call a node that is bounded on sort of the edge of the circuit, we basically start to finalize the search and then declare that the RTLIL primitives we've collected along the way belong to a single logic cone. And what this sort of looks like is here. So you can see a brief example of what Tamara will actually consider to be a logic cone, where you have this output, which is combinational, and then into a flip-flop, and then that gets bundled into a cone, and then the second cone can then start to be developed from there. After this as well, we also actually do the combinational replication, and this ends up being pretty straightforward once you've actually figured out all of the cones and stuff in your circuit. You can basically more or less just copy and paste them 3 times. But where it starts to become difficult is actually splicing the circuit to insert voters. I designed Tamara voters to always be single bit, but of course that's not true. You know, any complicated circuit is going to have multi-bit buses in it. So in order to handle multi-bit voters, I do a 2-stage process. Firstly, I ask the users to run the built-in Yosys commands, split cells and split nets, which is a bit of a hack and it does impact timing. But basically what it will do is it'll split up multi-bit buses into single-bit buses, or a multitude of single-bit sort of buses as best it can. And that'll, of course, apply it to cells and then nets. And then the remaining, basically, multi-bit ports, because you can still have ports on the edges of the circuit that remain multi-bit. These then get split apart by myself, and the voters are added to each of those bits. And then the voter generator comes in and basically introduces a reduce OR cell to OR together all the error signals in the cone. Because I forgot to add before, but basically not only do we add a voter to the cone, but we also add this error signal that's propagated through the circuit. And the error signal is basically set to high if it detects a bit flip. And the reason why that's important is because in a lot of cases, if you have an FPGA and you detect that you've been struck by a cosmic ray or some other bit flip has been induced, you want to reboot and reflash your circuit from a known good media. So in space, that will usually look like reflashing your circuit from sort of like radiation hardened flash memory or something like that. And those are usually radiation hardened by process, not by design. So those typically cost a lot more. But yeah, you can't really reflash an ASIC. You could reboot it though, and that's why the error signal is important. But long story short, the reduce OR cell gets added. All of these buses get ORed down together to produce a single sort of global OR, like, you know, has an error being triggered. And then we can insert that. Or in some cases, we cannot insert it. There are certain cases where you don't need to insert it. In single bit voter cases, you can omit it. And the reduce or cell is quite expensive, I imagine, at least. And so I can actually detect that and omit it. For multi-cone designs as well, the voter builder, as we talked about before, will basically need to emit this tree structure of OR cells to basically bubble up the individual error signal from each cone all the way up to a top-level error signal. And this actually adds a very, very long critical path delay. Essentially, in the worst case, a critical path delay from the input all the way to the output. So that's really problematic, but it's hard to do this properly without then introducing sort of, if you wanted to pipeline it, for example, that would change the timing, and so this gets very complicated very quickly. But I hope that made some sense. But yeah, in order to basically decide where we want to splice the voter in the circuit, we basically identify this thing that we call the voter cut point. And I determine this basically by, during the backwards breadth first search, I find the first node that is not the very first node in the entire backwards BFS, because that's when we enter the search, so that's going to be one of your ports. And it's not a terminal node. So in this case, I classify terminal nodes as IO nodes or flip-flop nodes. And it's also not a wire. There are some problems actually cutting on wires themselves. And so I try to skip wires. But any of these I identify as the cut point. And that's sort of the last bit in the cone where we actually want to splice in the voter. So what we can do then is go ahead and actually insert the voter straight away. We have this sort of template that's made out of C++ macros that we can kind of grab and just stamp into the circuit. And that works, but now we need to wire everything up together. And it turns out that ends up being the most complicated process. We want to basically connect the replicated elements output ports to the input ports of the voter. So the input port of the voter, as you might have seen all the way back in the intro, has A, B, and C as the input, which come from the three replicas, and then also an out, which is the majority voted signal, and then also the error signal as well. But it ends up being quite difficult to handle this in a lot of cases. There's issues where if a SIG spec is attached or not, if there's multiple SIG specs, we have to try and find the original output on the circuit before modification and attach to that. There's a lot of assumptions that I made here just for the sake of time, and I try to warn if they don't apply, or if these assumptions might be invalid. Anyway, basically, long story short, the wiring code is very complicated and kind of a total mess and doesn't really work that well. If the algorithm is continued, this would probably be the first target for something that should be rewritten. It's just really not that good. But it can handle simple-ish circuits, but very quickly falls apart if you have multi-cone circuits or any sort of complex, self-referential looping like RTL-AL. And of course, we can't actually handle all of the wiring in a single pass. We have to come back and do it again. So I introduced the concept of this thing called a fix walker, which is owned by a fix walker manager that basically tries to traverse the circuit in I think this time it's a breadth first order, and uses a callback system to basically apply individual fixes. I originally hoped to have multiple sort of walkers that would walk the circuit and fix them up, but I ended up only with one. And the goal of that is this thing called a multi-driver fixer that tries to fix cases where cells are driven by more than two or more wires at a time. So we try to look for cells that are driven by 3 wires, themselves drive 3 wires, and each of them also have a TMR cone annotation, which I add when I go through the BFS, or when I go through the backwards BFS and attach sort of voters and stuff to it. So that sort of looks like this. In the top, you can kind of see we have these 3 D flip-flops that are coming in and driving this single flip-flop wire, and then that flip-flop wire is in turn driving 3 of these logic NOT cells. And you can see that after this has been fixed up, the solution makes sense, right? We just omit this single middle flip-flop wire and connect them all up directly. I do believe that the wiring fix-up stage could be removed with just better wiring code, but I ended up with this architecture and it seemed to work kind of okay, so it's there for now. And so now that we've processed like a single cone, we basically need to think about how to continue the search for more cones. So if the input node of a logic cone that we just processed is connected to other cells, and those cells themselves we detected that we haven't explored yet as part of any of the other previous searches we do, then we basically add this to a queue of like things to explore. But it is, of course, important to keep a global sort of set of nodes that we've already explored, because otherwise in recurrent or like self-referential circuits, you can end up in this infinite loop. You can sort of imagine a pretty simple RTLAL example where you just have a square like this and it would just keep looping and covering itself again. So we try and avoid that. And that will sort of look like this. You can see we have this backwards BFS direction that goes through, and we have, if we're on this current cell here, we could detect a successor, and in that case, we need to go and continue and make another cone. But in some cases, we might not have a successor, and that's fine. We don't have to continue. So that basically covers the implementation of the algorithm, but that's only half the battle, because in safety critical sectors as well, verification is very important. So I tried to come up with a comprehensive verification procedure that uses a combination of formal methods, simulation, and fuzzing. And most of the formal method stuff is actually driven by Yosys's internal SAT solver. And one of the most important parts of this process is equivalence checking, with the goal of formally verifying that the circuit is functionally equivalent before and after the TMR pass. And that's important because we don't want this to change the underlying sort of fundamental behavior of the circuit. It should behave the same before and after sort of TMR is added. And also I do mutation coverage, where I basically want to formally verify that Tamara process circuits will actually correct faults that have been injected at a netlist level. And that's really important because it's basically a relatively good way of assuring that the algorithm does its job. And fuzzing is also a technique that I quite like a lot, coming from a sort of software background. So if you want to test at scale, fuzzing is a great way to do that. So I used Verismith to basically generate random Verilog RTL and then run the synthesis algorithm end to end, and then use sort of the SAT-based formal equivalence checking to verify that the random circuits behave the same before and after TMR. We would, of course, like to do mutation coverage as well, but if we want to do that, we'd need also valid test benches for these random circuits. And that would require automatic test pattern generation, or ATPG, which is sort of under active research and not something that I believe has been implemented open source in the literature yet. But it's a great topic for future research because it's a very important thing to do. Okay, so that basically covered sort of the implementation of the algorithm, and then we can talk about sort of how it went over the year and what worked. So the verification actually ended up working quite well enough. It's probably one of the better parts of the work. The results are relatively rigorous, and the fault injection with the mutate command worked really well. The mutate command is really nice to inject faults into the circuit. And fuzzing as well with Verismith, once I got it set up, actually worked quite well as well. There were some challenges though. I did have to drop using EQY halfway through the project due to its difficulties in sort of proving sequential circuits. So what I ended up with was reasonably long sort of manual scripts, Yosys scripts, using the internal sat command for equivalence checking. That being said, it did work well, and I was able to continue from there. And of course, this is not just a problem with Yosys, it's a problem in general. Minimizing fuzzer test cases is quite an arduous process, and it's on my list in future to write an automated sort of Verilog fuzzer minimizer for cases like this. So yeah, in terms of the programming itself, the code, I think, is relatively clean as far as research code goes. I had a bunch of scripts to automatically generate results, store them in JSON, insert them into a types document. So I wrote my thesis in types as well, and automatically then recompile it, which is very nice for end-to-end iteration. Stuff that would just like take you ages to do normally in a single CLI is just all integrated, which is quite nice. And you can do multi-threading as well over hundreds and hundreds of samples. So I was able to test, I think I ended up testing 8,192 fuzzer test cases, probably only in about 10 minutes. It is a massive pain to do in Python, but it's very much worth it. Colored logging, Yosys doesn't by default have colored logging, so I hacked in my own colored logging, which seems like a little thing, but is really useful for debugging passes that require a lot of sort of like printf debugging. And also having a regression test suite is really nice. The Yosys project itself has a very large regression test library, which is great. But when you're developing, your own sort of third-party plugin as well, it's also really important to have a regression test suite, I think. So what that sort of looks like here is you can see in this screenshot, I have this sort of fault injection sweep tool that will do fault injection sweeps through sort of a particular circuit and try and inject different numbers of faults with different circuit configurations using different sampling methods and different, circuit types, and it will dump that all to a file and then put that into my paper and then recompile it all. So that ended up being quite nice. And you can see the massive folder of them all stored here and all with their diagrams as well that are auto-generated. The show command in Yosys is really, really nice for this sort of debugging. It's a great tool. And you can see what that looks like side by side here. So if you ever want to develop a Yosys pass, which I think is a great idea and more people should definitely do, you can see what that ends up looking like here, where you have sort of your hacked in colored logging on the left-hand side and then a circuit. And I came up with a set of macros that would allow you to like step through the algorithm as it applies each thing one after the other. So that's really useful for catching bugs. And of course, the regression test suite as well is really important. I made a command that would run through all of these tests and run them. And it also would importantly keep track of what the results were the last time it ran, which means that it could tell you if you've actually regressed or not. So overall, the algorithm did end up verifiably working, with the caveat being it was for some circuits and some of the time. So you can see with these diagrams, this is a simple 2-bit multiplexer, and you can see that the orange circuit, if you can see it there, is just sort of at the bottom, and it's like 0% basically of faults that are mitigated. And with the TMR added, we can mitigate roughly about basically 60% of the time we can mitigate one fault injected into the circuit, and then it sort of falls off like this as you go through. And a similar thing is visible for the NOT gate as well, which is just a 2-bit NOT gate, although it is interesting here to note that for the two case injected, like 2 faults injected into the circuit, the unmitigated circuit, which has no voter in it, suddenly spikes up a little bit. And I think that's because basically the faults will kind of cancel each other out sometimes. And I was able to collect a decent breadth of results. So you can see here I've tried a bunch of different circuits. We've got multiplexers, sort of bit swizzling, bits and pieces of CRC circuits, just normal like combinational sort of test circuits. And these all have various different abilities, as you can see here from the graph, to protect against faults. And the similar case as well here on the right-hand side. So I was able to sweep with a bunch of different circuits and collect a bunch of different data, which is good. But of course, there's a lot of stuff that didn't work. As I mentioned earlier, I was initially unable to prove sequential circuits with EQY. Later, I was eventually able to prove sequential circuits, but I ran into more difficulties because of some very strange behavior with fault injection on D flip-flops. So as you can see here, when the number of faults increases, a completely unmitigated circuit with no voters at all somehow becomes almost approaching 90% effective at mitigating 9 faults, which is completely bizarre. I'm still not sure entirely why this is the case, but I believe it's probably because of a very complicated interaction where accumulated faults that are injected into the circuit will cancel each other out and that type of stuff. And initially in my verification, I didn't have a lot of test coverage, which is a common thing, but later I was able to fix that, which is good. Of course, there's a lot of issues sort of with the algorithm and just developing the algorithm. I did find it hard working with Yosys RTLIL. Yosys itself is a large sort of older style C++ code base, and it's great that Yosys has been around for so long, and I mean no hate by this, purely just an observation that it's a large, chunky, older style code base. It does take some getting used to and a lot of like jumping around to see where things happen. The Yosys user-facing docs are excellent, but there's not many docs yet in terms of like internal stuff about how RTLIL does things and passes and things like that. I'd like to work on fixing this, and that's something I'd like to do to sort of go through and sort of, now that I've pieced together a bunch of stuff, sort of add like inline doc comments and get a doxygen generated and that type of stuff. That would be very useful. It was also, for some reason, for me, quite challenging to initially understand how to find which nets are connected to each other in a circuit. So I probably didn't end up doing that the correct way, but that was a little bit hard. Splicing and rewiring circuits ends up being very complicated to handle correctly in all cases. And that's mostly because RTLIL is validly very complicated because it has to handle all sort of Verilog, VHDL, any sort of HDL constructs. But that does mean that, when you want to rewrite a circuit and splice things in, it ends up getting sort of quite complicated quite quickly. I did actually as well also, I ran into an upstream Yosys bug, which I luckily was able to minimize from the fuzzer report and actually have fixed, which is sort of shows, I guess, the benefits of like FOSS and why it's great to have a good community like this, because people find bugs, bugs get fixed. It's going to be much faster than you can get with like a proprietary vendor. But yeah, that did block me for a little bit, but it's all good. And of course, there are a huge number of my own bugs, many of which remain to this day, including the ability to not handle multi-cone circuits, which is very essential in sort of any even moderately complex design you get. And that's just caused by very complicated issues with like the mess of wiring code and sort of how to extract things out and rip them up and put them back together again. So you can kind of see what's going wrong here. There's like bits and pieces of the circuit, and these should be wired up here, but they're not, and it's like all complicated, but that's okay. And there's other bugs as well, where like multiple voters in the same logic cone still cause multi-drivers on the output, and multi-drivers are not really that valid in Yosys, which I tried to fix with the multi-driver fixer, but that in turn can crash on some designs because that whole thing is a hack and wasn't written particularly robustly. So that should ideally be rewritten. And there's kind of test cases that fuzzers will find that aren't really that, like, I kind of describe them as adversarial in that they're kind of insane. Like, why would you write RTLIL like that? But nonetheless, they cause the algorithm to crash, which is valid and, needs to be fixed. So the end result, of course, is that although we can handle some circuits and we can prove that it does work a bit on some circuits, we can't really yet handle anything real world adjacent yet, which I think is important to stress. And of course, the underlying causes being that RTLIL netlists are very complex. Splicing is complex with all the edge cases, and I like to compare it to writing a compiler optimization pass in sort of the level of like edge case and stuff that you need to handle. Yosys internals are not yet super well documented, but I also must really stress here that I didn't do enough of my own reading as well. And I think I'll get into that a little bit more later, but and chiefly as well, just a lack of time. I think a lot of these issues would be fixable given like another 6 months of programming, but in research we're on a deadline and I had to sort of release the paper. So yeah. But the ultimate fix for basically all of the problems is more or less a sort of big rewrite in terms of handling things the way Yosys wants them to be handled and not sort of in my own way. I do think that the project is not a dead end. I think that we have some promising results so far. We clearly can help to mitigate some circuits some of the time. So it's definitely probably a good spot for future research if it's desired, but currently can't target like, production use cases. So in the end, of course, I was aiming to publish, but it didn't end up being suitable to publish just because it can't really handle anything that's equivalent to state of the art. So a paper that I mentioned earlier from Johnson from Brigham Young University, they can handle sort of moderately, I think like decently complex circuits, but their downside is you have to export the circuit into EDIF and then run it through their tool and then import it back again. But still, because I can't handle that, it didn't end up really being that publishable. And hence why I've sort of slapped a towards in front of it and given talks on it. But anyway, what are the main takeaways from research and my research about TMR and this type of stuff? I have come to the conclusion that I think at least TMR is probably not the answer if you're looking to design rad-hardened microprocessors. The trade-offs are just very poor. You at least increase the area requirements by 3 times. And in the case of Tamara, you severely increase the critical path delay. This isn't totally necessary. There are papers that use complicated synthesis techniques like HLS to basically, they can use HLS where timing isn't sort of as fixed as it is in HDLs to reconstruct the circuit and distribute some of those delays. But in Tamara's case, the critical path delay from the input to the output with the error signal can get very, very long, and that's very bad. As we've seen, it's not necessarily even that good at protecting against faults, particularly when we don't consider physical placement as part of the process. So this is all still operating at the netlist level, and hence, not at the placement or the routing level. So we haven't yet considered any sort of physical placement as part of the process. I think TMR still could be useful for analog circuits or digital circuits with no other way to introduce redundancy. For example, maybe if you have a encrypted sort of HDL block from a vendor like Xilinx or something like that, and there's no other way to introduce redundancy other than copying and pasting it 3 times, that could be potentially useful. But if specifically you want to design rad-hardened microprocessors, I think there are better techniques out there in terms of error correcting codes and things like that. However, if you do want to do TMR, I think netlist level redundancy is likely still the best option trade-off wise, although I will say that design level approaches would have probably been easier for me to write. The main problem with design level approaches, at least under Yosys, is that there still isn't any clear way to basically flag that these replicated elements shouldn't be removed. They should be kept. I'm tracking some PRs with Yosys, I think George might have put up, where they're going to sort of have like a optimization, please ignore this cell annotation, and that would totally solve this problem. And then in that case, it would flip around and design level approaches would be very good. But until that is sort of the case, and I don't believe that's common with even commercial tools as well, it's very hard to ensure that those cells don't get removed. And also, the advantage of netlist level approaches is they can handle any input HDL. So if you want to write in VHDL or Verilog, you don't have to worry about that. You can just sort of, publish it in and it will deal with it. You could, of course, do sort of a design level approach in sort of like a mid-level, like maybe in sort of a syntax tree level, but that might be interesting to look into. But yeah. In terms of design level approaches as well, if you are going down that route, modern HDLs outside of Verilog, like Chisel or Spinal, might provide easier ways to actually do this sort of design level TMR copying and pasting, other than just physically copying and pasting through things they have, like macros and functional programming and stuff like that. But in terms of the actual algorithm itself, reflecting on it, I didn't do enough sort of rigor reading the Yosys code, and I think that was one of my big problems. I actually based the majority of my code's implementation on the Booth multiplier pass, because I thought that was really cool and it was fun to read. But that's a pass that generates logic cells rather than modifying or splicing existing net lists. And so because of that, I didn't understand properly how to modify and splice netlists. Whereas what I really should have done is go from the start reading optimization passes. I think that would have been much better. And sort of my general approach as well, I pretty significantly underestimated the complexity of the project, which I'm trying not to do for the PhD. I rushed into programming too quickly, and ended up in a hole and just kind of went back and forth, like hacking and trying to fix things. It's always smart when you're designing passes like this to kind of take a step back, and because the most obvious solution is often not the correct one. And another thing as well is that, sort of like coming into this with lofty expectations, being like, oh, I'm going to rad harden a CPU, meant that I was kind of ended up setting up myself up for disappointment. And it's probably often better to focus on a small goal and be happy to achieve it, rather than being like, I'm going to do this amazing thing and then not being able to achieve it. But anyway, let's talk about what's next on the horizon for sort of radiation hardening and where I'd like to go from here. So next year, I'm applying to join Macquarie University's Silicon Platforms Lab in Sydney. So I'll be moving from Brisbane, and I'm hoping to start that February next year. The cool thing about SIP is that they're the only lab in the whole country that of Australia that focuses on digital ASIC design. There really is nowhere else you can go to do that type of research. I'd like to aim to continue my research, sort of taking the next logical step to build EDA algorithms for harsh environments. And as I talked about earlier, I think it's really important to consider the physical characteristics of the circuit, which is why I'll likely be moving into PNR for ASICs, so mostly open road. But still, despite this, FOSS for me remains my passion. I want to continue using and contributing to Yosys, open road, and other tools. So I guess the main aims are, as I said, to keep using open source EDA tools. And I think importantly for me as well, I'd like to demonstrate the importance and effectiveness of open EDA to research. I'm sure we all agree on that in here, but a lot of papers are still published that are hacking on proprietary tools like Synopsys, and a lot of labs can't afford those expensive tools. So I'd like to show that a lot of research can be done using open tools. And basically, the overarching goal is to do challenging sort of domain-specific EDA algorithms for niche sectors. And space and rad hardening is the main one that I'm thinking of. The general idea from here for me is basically to integrate statistical models into the EDA tools to better understand the operating environments that the chips will be deployed in. And I'd really like also as well to deploy something on Tiny Tapeout or another multi-project wafer, and ideally perform physical radiation testing on that chip, because we do have the facilities here in Australia to do that at ANSTO's particle accelerator. So one of the ideas I've had is basically using a physics-based understanding of the way SEUs strike CMOS transistors to basically guide placement for ASICs. So what you could do is develop sort of this fast statistical model based on data that understands how to place things on the chip, and then use that to inform the global placer algorithm. And then you can strike, in a very difficult process, you can strike an optimal trade-off between performance, power, area, and radiation tolerance. But an alternative idea is also to look into sort of the more cybersecurity area with side channel and voltage glitching attacks as well, because it might seem like a bit of a detour, but these side channel and power glitching attacks have a surprising amount in common with radiation hardening. And it's true as well that security processors are obviously more deployed than space processors. They're a lot less niche, so there's potential more research applications there. And the idea is similar to the last one, but using a model to understand side channel leakage and voltage glitching. There's a lot of research on side channel leakage, but basically none on voltage glitching yet, despite the fact that voltage glitching remains a real attack that was used, for example, I believe, to glitch the bootloader of the Apple AirTag. But certainly this is very challenging because it's much more difficult to model sort of a side channel than SEUs. For space stuff, your radiation is not sentient, so you don't have the problem of them being, crafty fellas. Whereas for cybersecurity, your attackers are of course sentient, so that adds a whole level of difficulty to modeling. But yeah, these are some citations, just the references that I've used if you want to have more of a look at sort of TMR and the literature that I cited. And that concludes my talk. So if you want to email me or visit my website or GitHub, you can. And you can also read the blog post that I put up on the Yosys blog. So yeah, I'm happy to take any questions. Thank you so much for listening.